We're going to begin a discussion of finding derivatives of logarithmic functions. So let's first quickly remember what a logarithmic function is, or a logarithm. So some examples of logarithmic functions. Okay, for instance, we might have f of x is equal to ln of x, natural log of x. That's what that ln is for. And in this particular logarithm, we talk about the base of the logarithm being the number e. Say another way to write this, although we don't, we use this shortcut, is f of x is equal to the logarithm of x base e. And of course, like I said, we choose not to write it that way because that takes more work. It's that simple. We just have a shortcut notation. We might have g of x is equal to the natural logarithm of 3x minus 5. That would be, again, the base is e. Now, the base doesn't always have to be e. Okay? For instance, we could have h of x is equal to the logarithm of 2x to the 4th power plus 1, base 3. Of course, as I said, in this case, we have a logarithm of a different base. In this case, the base would be 3. Now, there are times that it's important to use other bases. We could use any base as long as it was a positive number. Okay? And we're usually not interested in base 1, but any base other than 1 that's a positive number would be a potential base. But for our course, the focus will be on base e. So although there's some other bases that are used in your book, we're going to concentrate on base e, and so we'll always be talking about a natural logarithm. It will be things like this that we see. Okay, well, of course, this is about derivatives. In a business calculus class, or a calculus class for business and social sciences majors. So let's write this down, that if we have a function f of x, we'll start with the simplest of functions, is natural log x. And sometimes we just put natural log x, or ln x, recognizing that the x there is the argument. Sometimes I might forget. To do it accurately, we really should put parentheses around the x there. Okay, well, if we have a function f of x, which is natural log of x, then the derivative of that function is 1 over x. That's the derivative of the function. Now, of course, an alternative way to write this, an alternate way to write is without the function notation at all, and that's when we say the derivative of. See, the derivative of natural log of x with respect to x is simply 1 over x. Now, that's not going to be very interesting, quite frankly. See, that takes care of the function f of x above, but that function g of x, it wouldn't take care of, would it? See, because this just tells us how we take the derivative of natural log of x. It doesn't say anything about natural log of 3x minus 5. So, like I said, another example, the other example we have above, g of x equal to the natural log of 3x minus 5, this doesn't tell us how to do that. This is not enough. It's not enough to decide what the derivative is. And so we're going to have to introduce some more information. Before I do that, I want you're going to hear me say this word, so I want you to recognize when I say it, what I'm referring to. That 3x minus 5 is what we're taking the derivative of. Excuse me, the natural logarithm of, pardon me. And that 3x minus 5 is called the argument. That's what that's called. Okay? So argument means that's what we're taking the logarithm of. Now, to deal with the problem, to deal with g of x, we've got to remember the chain rule. See, the chain rule is required to find the derivative of g of x. Well, just say to find g prime of x. We know that means the derivative. Now, let me remind you of what the chain rule says, because let me remind you what the chain rule says. It says that if we're given a function, or if we have a function f of x that is the composition of two functions, that is, we put one function u into another function v, that's what our function f looks like. In that case, the chain rule says the way we find the derivative of our function is that we find the derivative of the outside function and we put the inside function into it. But we have to multiply it with the derivative of the inside function. Now, the way this worked when we were dealing with only polynomials, we were talking about the outside function being parentheses with a power on it. And the inside function was what was inside the parentheses. And so that ended up being the general power rule. And then we finished just talking about, in the previous section, finding derivatives of exponential functions. Well, the outside function in that case ended up being the e to the x power. And the inside function was actually what the power was, and it wasn't just x. And so when we took the derivative, we had e to the original inside function, that is e to the original power, and then we had, say, times the derivative of the inside function. Well, the inside function was, in fact, the power. So we've used this chain rule and had special circumstances two different times now. And that's what happens here. We're going to have another application of the chain rule specifically to logarithmic functions. And we'll continue this on the next page. So when we're, as mentioned, when we're talking about logarithmic functions, the chain rule is applied just a little differently. I mean, it's all a chain rule, but it looks different because of the way we're specializing. So let me write out this way then. So suppose f of x is the natural logarithm of something, okay? And rather than calling it just some expression, I'm going to call it the argument. Remember, the argument is what we're taking the logarithm of. So f of x is equal to the natural logarithm of the argument. Well, then the chain will say the natural logarithm is the outside function and the argument is the inside function. So the chain rule tells us that the way we would find this derivative is that it would be the same as the derivative of natural log of x, but we put the inside function inside of that. And so that means instead of an x in the denominator, we actually have the argument. So 1 over the argument instead of 1 over x, and then times the derivative of the inside function. Well, the inside function is, in fact, the argument. Okay? So that's the way the chain rule would tell us to do this. And maybe that sounded confusing. Let me write it just a little bit differently here. So it all says the same thing. That if we have f of x being the natural log of something that we're taking the natural log of, the u of x is just the inside function, then the derivative is nothing more than 1 over what we're taking the logarithm of times the derivative of what we're taking the logarithm of. And you've seen that times the derivative of the inside is what happens in the chain rule. We see that appear over and over and over again. Well, let's do a specific example here then. In this case, f of x is the function natural log of 2x. Okay, and we're to find f prime of x. So the way we go about that then, of course, if f of x was just natural log of x, then the derivative would just be 1 over x. But we've got to use a chain rule because it's not natural log of x, it's natural log of 2x. So we approach it this way then. F prime of x is, now what's it say? 1 over the argument. See, 1 over what we're taking the derivative of, and then we have to multiply that with the derivative of whatever the argument is, the derivative of 2x. And in this case, of course, that's 1 over 2x. The derivative of 2x is 2, and so that's 2 over 2x, which of course simplifies to just 1 over x. So strangely enough, in this case, we also get the result of 1 over x. I think in the next case we won't. So let's look at the next example. In fact, let's look at the example that I really kind of got out of order, and that was our g of x. Okay, so in this case, we'll say g of x is equal to the natural logarithm, and what was it? 3x minus 5 was our argument? I believe so. 3x minus 5. Okay, find g prime of x. Okay, well here we go. It's pretty easy really. G prime of x is 1 over the argument. The argument is 3x minus 5. Then don't forget to multiply with the derivative of the argument. Of course, that means the derivative of 3x minus 5. Well, that's not going to be difficult because the derivative of 3x minus 5 is nothing more than 3, isn't it? So that's just a 3 that we're multiplying with. And of course, that would give us 3 over 3x minus 5 when we multiply those together. So this one was a little more complicated looking example, or a little more complicated result than what we got a moment ago. Let me move to the next page and we'll increase the difficulty some more. Okay, here's our next example. Find dy dx, or the derivative of y with respect to x, if y is the natural log of 2x squared plus 4. So we recognize we're going to have to use the chain rule right away because it's not natural log of x, it's natural log of 2x squared plus 4. So finding derivative of y with respect to x would go this way. Derivative of y with respect to x is 1 over the argument, and the argument is 2x squared plus 4, and then multiply with the derivative of the argument. Now, let me point out to you that I recognize that a lot of you, that you may be in the position that you don't need to write down this portion that we've written down here. I mean, it's going to have to be included, but you might be able to do that on the fly. That is, you might recognize before you write down derivative of that the derivative is going to be 4x. And so you could just say times 4x rather than writing all this notation. And I don't have a problem with that, but be sure that you can write this notation because there will be problems here and in the future where we have to be able to write the calculus. Otherwise, we'll never get the problem done because there's too many steps. So anyway, here we go. 1 over 2x squared plus 4. The derivative result, of course, is 4x plus 0, or just 4x. And then that would give us, what, 4x over 2x squared plus 4. Now, another issue with math, or almost any topic, is you always have to be vigilant, that you always have to be on the lookout. You get real proud of yourself for doing the problem, and then you don't think clearly, or you don't think it through to the end. And whenever we have a fraction, we need to be concerned about whether we have that fraction written in its simplest form. In other words, we don't like to write 10 over 2, we'd rather write 5. We don't like to write 6 over 9, we'd rather write 2/3. And the same case happens when we're dealing with fractions that involve variables. So we need to consider whether this can be reduced. Now, a common mistake that is made, and let's just be clear here, a common mistake that's made, and I hope you're not in this category, is that we see the 4 on top and the 4 on bottom, and we want to cancel that, okay, and say, oh, well, that's just going to leave us with an x on top and a 2x squared on bottom. And, well, now, if we do that, then we could cancel here, and that would leave us with a 1 on top and a 2x on bottom. But that's wrong from the beginning. That's completely wrong all the way through, okay? Act like I didn't even do that. And let me kind of remind you of why that's the situation. If I asked you what 5 over 10 plus 5 is, and you can look at that and say that, oh, well, that's really 5 over 15. See, we really know that that's 5 over 15. And we know that 5 over 15 would reduce to, what, 1/3? See, that would reduce to 1/3. Now, the wrong thing to do is to cancel this 5 and this 5 and say that that's equal to 1/10. See, that's the wrong thing to do. That's not true. And the reason we can't do that is you can't cancel unless both the numerator and denominator are in factored form. And we didn't have that here, and we didn't have it above. See, we didn't have it above up here. Things were not, the denominator was not in a factored form. We pulled out a term and canceled it, and that's absolutely not allowed. You can see that here. So if we were going to try to reduce this, we need to look at the numerator and denominator, and particularly the denominator, and see whether we can factor the denominator. Well, I'm looking, and I see that 2 is a factor of 2x squared, and it's also a factor of 4. So 2 can be factored out, and we would have x squared plus 2. And of course, in the top, we've got 4x. And we usually would leave that alone, but since we've got a factor of 2 below, we'll write 4x as 2 times 2x. Then we can see that cancels, and we would end up with just a 2x over x squared plus 2. And the 2's are not cancelable. That would be the way we should leave our answer. If we left our answer like this, then my math lab might count it wrong because it's not reduced. Okay, let's look at another example here. Let's see what I've got. Oh, this one probably will take some work. In fact, I think this will probably take a lot of work. Let's see if we can do this one, okay? Here's the example. Here's the statement of the problem. Okay, we're to find f prime of x if f of x is the natural log of the square root of x plus 1. Now, I'm shuddering thinking about this already because I'm thinking in the chain rule, we're going to somewhere down the road need to find the derivative of the square root of x plus 1. Now, I'm not really shuddering, but I know that maybe that's what you're doing. But let's go ahead and let's have at this. Let's see what we can do here. So to find f prime of x, what do? We say 1 over the argument. Now, in this case, the argument is the square root of x plus 1, the square root of x plus 1. But then we say multiply that with the derivative of the argument. So that's the derivative of the square root of x plus 1. Well, it was easy to write that much, but here is one of those cases that we can't calculate the square root of x plus, the derivative of square root of x plus 1 in our head, and that was the reason it was important to be able to write it down. Now, what I'm going to do is I'm going to come over here to the side, rather than interrupt the flow of my work here on the left, which I'm finding the derivative, remember, I don't rewrite that f prime of x over and over, but I'm going to come over here to the side and concern myself with finding the derivative of the square root of x plus 1. That's almost like a separate problem. So I'm just going to put that part over here, say, well, how do I find the derivative of x squared plus 1? And it wasn't long ago that we were doing things like this as the whole problem. Now it's just part of a problem. Now remember, one of the basic tools we have, or one of the tools we have, is the general power rule. And we remember that square roots or radicals in general can be written as powers, so we can change this to the derivative of the x plus 1 to the half power, to the 1/2 power. Then the general power rule applies. So we would bring the 1/2 down as the exponent, but we would create the new exponent. And so that would be the old exponent subtract 1, which is a negative 1/2, isn't it? So our new exponent would be negative 1/2. But then we have to remember this is the general power rule, okay, which means it's a special version of the chain rule. We have to multiply that with the derivative of the inside. Well, in this case, the derivative of x plus 1 is just 1. So it ended up not being a big deal, but it could have. Okay, that is really a 1. So the result we have here is 1/2 times x plus 1 to the negative 1/2 power. So over here, in the place of that derivative, you see we have a 1/2 times x plus 1 to the power negative 1/2. Now, let's not forget that we don't like to leave answers with exponents that are negative. So as we go forward to do some more algebra here, we need to rewrite that negative 1/2 power as a positive exponent. So we have the 1/2 in this case, and here we would have 1 over x plus 1 to the positive 1/2 power. Now, let's look what this results in, okay? Because this is let's see. Why don't we put this 1/2 in front completely, and then we have 1 over the square root of x plus 1, and then we recognize we're going to go backwards. An exponent of 1/2 means a square root. So this is 1 over the square root of x plus 1 again, isn't it? And then it should become clear that what we're going to have is, in the denominator, in the numerator, we have a 1 times a 1 times a 1. In the denominator, we have this 2 times root x plus 1 times root x plus 1. And when we multiply the same root together, it's like squaring it, isn't it? And so the result we're going to get is just x plus 1. And remember, that's since what we really have here is the square root of x plus 1 being squared, since we're multiplying those two together, which just gives us the inside, doesn't it? So our final answer, after a lot of work, the derivative of this function is 1 over 2 times the quantity x plus 1. Now, my intention at this point is to show you how we can do this problem easier. In fact, show you how we can do some of the other problems easier if we apply laws of logarithms. So on the next page, I'm going to remind you of what those laws of logarithms are, and then we're going to redo some of these problems using those shortcuts. In fact, what I'm going to do is stop this part and create a part 2. So we'll stop this completely and we'll start up fresh in another video.